Hi everyone, we are Group 7 and here's our L2 project. So, a recap of the tasks that we are given. First, design a horizontal axis wind turbine with 2 blades. Next, to make sure that it has self-starting capabilities at 10 meters per second wind speed. And finally, achieve high CP with low weight. So we set on this task, and after months of design, manufacturing and testing, this is what we have. Let's first look at the design, but before that, some theory. A wind turbine works when its lower surface faces the incoming wind. With the induced velocity due to rotation, we have the net wind striking the airfoil at an angle of attack. Hence, lift and drag is created as shown. To keep rotating, we need to maximize the component of lift in the right direction. Hence, good wind turbine airfoils must have high lift over drag ratios. And with this in mind, we start shortlisting our airfoils. First, we search the web, and we shortlisted 2 airfoils, the S833 and the SG6043. Next, we analyzed both using online tools, and we found the characteristic plots of both airfoils. Notice that regardless of Reynolds number, the SG6043 gives higher lift over drag ratios. And so finally, we choose the airfoils, and you would have guessed it, we picked the SG6043. With the airfoils shortlisted, we went to fixed chord distributions next. We had to pick our TSR first. Now, we wanted a TSR to balance both power and strength. For small wind turbines, the ideal TSR is between 4 and 5, so we decided to start with 4. Next, using Schmidt's equations, we produced a series of chord and pitch distributions. We didn't just do one distribution, we did a few by varying TSR slightly. And we found that for TSR range between 4 to 4.2, selecting 4.1 gives us the best CP and reasonably low weight. Next, we check for potential modes of failure. As a result of the dynamics of a wind turbine, there are 2 potential modes of failure which may occur. The first mode, where it fails along the plane of the blade, is related to centrifugal forces. The second mode, where the blade fails perpendicular to the plane that it's in, is related to aerodynamic forces. The blade will fail at its weakest point. Due to the taper of the blade at the inboard area, this is most likely to occur at the root of the blade. The centrifugal force acting on each point of the blade is proportionate to the sum of centrifugal forces acting on all elements from that point onwards. The stress can be found by dividing the force by the surface area of each corresponding element. This can then be analyzed by comparing with the tensile yield stress of the material. It is clear that the stresses caused by the centrifugal forces is much less than the maximum yield stress and hence would not cause the blade to fail at any point. The lift and drag forces acting on the blade can be combined and treated as one total aerodynamic force. The component of this, which acts in a direction perpendicular to the direction of motion, will result in a bending moment about the center of the turbine. This can then be converted into stress using the bending beam theory. The second moment of error for an airfoil section can be calculated as shown. The stresses are then analyzed again with the peak tensile failure stress of the plastic. Here, we can see that the stresses at the root will exceed the yield stress. Therefore, further strengthening will be applied in the final design considerations. The deflection caused by the aerodynamic forces results in a similar plot to the stress curve. Final design considerations. The blade. Studding. As the plastic alone would not be able to withstand the aerodynamic stresses, adding studding would be necessary to strengthen the root of the blade. Align chord at quarter point. The elements with the chosen chord distributions are aligned relative to each other at the quarter chord point to ensure taper on both sides of the blade. Inboard taper. The inboard area of the blade is tapered into the hub as the aerodynamic effects of this area would be negligible. Lastly, rounding of blade tips. The edges of the blades are rounded in order to reduce drag at the tips. This is based on the principle that elliptical wings have the highest efficiency compared to other designs. Next, we looked at the hub. The design of the hub was chosen to minimize weight. The simple, functional design of a cylindrical shape with 2 flats directly opposite each other was chosen. It is symmetric to maintain the balance of the turbine. The dimensions of the metal hub, along with the outer plastic hub which surrounds it, are determined by the minimum thickness possible in order to reduce weight while not risking failure. Threaded holes on the sides are made for the studding and grab screw, along with the required through hole for the main shaft and keyway. Lastly, self-start. The self-start capabilities of the turbine is determined by the aerodynamic moments of the blade compared with the moment of friction forces in the gears. The relatively large surface area of the design and twist at the root will inherently provide a large aerodynamic moment for the blade to self-start even at low speeds. Once the chord distributions and characteristics are finalized, the components are drawn through Creo. The drawings are exported and printed for submission. All the components are created in accordance to the British standard BS 8888 and displayed in third angle projection. Due to limitations of dimensions the 3D printer can print out, the structure was divided into pieces for manufacturing. For simplicity, only the overall drawings of the key components are presented, alongside with projected drawings in Creo. The entire structure was shown on an exploded view page in here with all necessary information. Next, the blade is printed using 3D printing. The print head sweeps through a layer of materials and the shape was built up gradually in one layer by another. All components are made of ABS plastic. Before combining the parts of turbine blades together, the aluminum hub was to be shaped, which is a key element in between the rotating shaft and cone. The outside of the hub was cut off steadily to avoid overheating. This was followed by boring and parting of the hub, in which the processes have to be cooled down by spraying some fluid on the heating surface. After that, the hub was ready to be drilled to allow studding through the center. Here, we have a sequence of pictures to show how we glued the parts together. They were bound together by superglue and clamped to fit in place. To preserve the smoothness on the surface, which affects the performance, the blades underwent some sanding. And finally, everything is on their way and off we go for testing. Let's now take our wind turbine to the Honda wind tunnel in Imperial College to test its self-starting capabilities and performances at various wind speeds. Here's a summary of the wind turbine performance at different wind speeds. The graph shows how the power varies with the RPM of the turbine at each wind speed. Using the plot, we are able to obtain the maximum power at each wind speed, as well as the max CP at its corresponding TSR. Due to careful structural considerations during the design stage, the wind turbine was able to survive the 12 meter per second wind speed and provide maximum power of 125 watts. Which was enough to power 4 Philips light bulbs. Quite remarkable for a small-sized wind turbine. Next, we evaluate our design by comparing our expectations with the actual results. There were two main discrepancies which we need to account for. Number one, weight calculated using Creo was significantly lower than actual weight. The density of the ABS plastic given for calculations might be inaccurate, which led to the discrepancy in the actual and theoretical weight. There's also the limitation to the precision of 3D printing. During printing, it is impossible for the printer to reproduce the same movements between layers. This led to uneven roughness on the surface of the prototype made, which contributed to the weight discrepancy. Second, deviation in terms of the TSR at maximum CP. This is mainly due to the deviation between the Q-blade simulation and actual experimental conditions. Wind tunnel effects, which affect the flow properties and hence the CP, was not taken into account. Furthermore, Q-blade simulation was unable to account for losses such as tip loss and flow separation. As a result, we designed the wind turbine meant for a lower TSR. Overall, the wind turbine performed well aerodynamically by achieving high CP. However, our merit function was affected by the turbine's heavy weight. Hence, our main improvement will be focusing on weight reduction. Studding contributed a significant portion of the weight. We believed studding can be removed if we choose a more circular airfoil for the root section. Since our TSR at maximum CP is higher than expected, we can design the chord distribution of the blades based on a higher TSR, which will produce a more slender blade and reduce the weight of the prototype. In the end, we are glad that our wind turbine survived the highest wind speed tested and delivered reliably good power. The L2 project has been a journey of self-discovery, fun and fulfillment. Well, we hope you have enjoyed our presentation and thanks for watching.